All right. All right, hello everyone. My name is Fumiya Ida. I'm a professor of robotics, and here I'm with Dr. Thomas Tutel. He's a senior research associate working on Workbench 4, Robotics and Automation of the Digital Road and Future Roads project. So just to give you a bit of background of ourselves, so our previous life before Digital Roads was that we did bio-inspired robotics. So we're interested in the fundamental difference between biology and machines, animals and machines, and what makes them different. And we want to learn from nature to improve technologies, but at the same time, we want to do biology by using engineering technology. So we're doing something completely different from this project we're planning to do. Just like many other big head Cambridge academics, we do how to do equations and lots of things, but we don't really know how to make roads and infrastructure. So we're not even pretending we know it, but it was really hard time last 6 months, 1 year to learn what's actually going on in this civil engineering and the road industry and how we could be useful for this kind of project. And but in the end, it was a really good opportunity for us to learn what is this actually, and then this is what we're trying to present in the next 20 minutes or so. All right, so Work Package 4 is mostly about monitoring, sensoring, and the maintaining and the repair and the simulation of robotic systems. Because the road industry is a very big and challenging problem, so we cannot do everything at the same time in a short period of time. So what we're trying to do is really focusing on how we can apply sensing and monitoring technologies by using robotics and automation technology. So that's what we're trying to do in Task 4.1. What's actually the necessary procedures in monitoring, fall detection, and so on. And then the task 4.2 focusing more on sensor systems, like what's the state-of-the-art sensors, how we can improve it based on our technologies. And then the 4.3 is more about the data-driven robotics. So this is kind of connection with the digital twin work package and also data science work packages. Okay, so what is robotics and automation in the first place, right? So this is something we need to go back, step back a bit and think about the fundamental questions about what is robotics, what is automation. It's not just applying some gadgets to the field and see what happens, right? So this is a little more systematic science, and it's actually system science is the backbone of automation and robotics. So automation robotics, we're usually thinking about sense, think, act cycle, right? So assuming the system is integrated in the road or whatever physical systems, and there we have a smart materials out there, but then we want to apply some sensing technologies to perceive what's out there in the world. And then the control learning simulation, this is the kind of thinking process, what system should do, system should think about, take actions, and then we actually implement actions. So this includes planning of actions, what it should do, and how we should do. And then actually we put it in the actual device that actually take actions. The action part is actually quite important in the whole framework because this is not touched by any other work packages of the Digital Roads project. But it's not only about actions. Actions related to some, the devices and infrastructure in the environment, but the whole thing behind it is actually integrated. So this is a system science of automation and robotics. And what we usually talk about is the so-called embodied intelligence as opposed to computational intelligence. So we all know that the AI is giving a lot of impact in our society, but the AI is usually about the computational intelligence. We're thinking about how to process information, how to make use of information, but the embodied intelligence is actually physical input, physical output. We need to think about how physical reality of this world, has to be somehow captured as an information. But then, in the end, we need to really take actions in the physical sense rather than just stop at the information processing. So that's the kind of whole process that we want to look at. So, and there are lots of challenges from embodied intelligence point of view. And that's what we're going to talk about in this digital roads project. And obviously, digital twin and data science are related to this project, but this work package, but also the smart materials that Abby talked about was also coming down on the opposite side of it. So this is a really a kind of, the parallel process with all other work packages, and we really need to work together with other work packages. That's the main point of this robotics and automation. Okay, so what's actually going on? So what we did, what we have been doing in the last 5-10 years is really about trying to take advantage of technological advances. What's the game-changing technologies? What's the enabling technologies to make a bit of impact in the real world? And what we are experiencing at the moment is a lot of things related to data-driven sensing. So AI is actually the driving force of robotics. So we do a lot of data-driven sensing, and of course, the materials is another really big driver of the technological innovation. If we don't have a new materials, we cannot build the new technologies. Along with that, the physical simulation and computer graphics is actually a very exciting venue that we need a lot of data in our machine learning, but the data cannot be captured all the time using sensors. So we actually need to synthesize the data by using computer graphics and computer physics simulation. And then obviously a lot of other enabling technologies like autonomous driving, dexterous manipulation, drones, like robots, wearable technology. So we did quite some agricultural project in the past, and we are doing also a lot of the manipulation task for the cooking and quality control. And then we have some wearable technologies based on our spin-out collaborations. So what is the theoretical ground challenges of automation and robotics? So we talk about the sense, think, act as the basic ideas of robotics and automation. But what we need to think about in the 21st century is really how do we go beyond sense, think, act cycle. Instead of sense, think, act cycle, we really need to think about what we call surprise, adapt, and predict. Right, so we usually start with the prediction because we have a lot of data-driven science that we are able to predict what's going to happen in the near future or long-term future. But then the prediction always ends up with surprise, and that's a very important emotional reaction if you're biological systems, right? We always surprise, and surprise is a very important trigger that we need to learn and we need to adapt. So this is, of course, very similar to sense, think, act cycle, but it's fundamentally different because the prediction is the basis of all other things. And that's something we really need to put as a vision of the automation and robotics, and how we can do predict, how we can do adapt, and all of these things are on top of the digital twin technologies and data science technologies. And then eventually we need to plug in sensing and robotics systems in this. So, and of course, in order to do the prediction, we cannot sit with the conventional technologies because, prediction needs a lot more data, a lot different kind of data. And here we talk about large-scale, low-cost, multimodal, redundant, active sensing. So the sensing has to be completely different from what we used to think about. It's not just sensor put somewhere and expects this sensor will give us something useful. But we need a different kind of sensors and different kind of low-cost sensor possibly to cover large areas. And the multimodal, right? I think Abir already talked about many different sensing modality is already actually possible. So that's something we should take advantage of. What's new in this is active sensing. So we need to do the prediction-based active sensing. We need to go and get the data we want rather than wait and hope that the data arrives, right? So that's another way of thinking about prediction-based and active sensing. And simulation for prediction. So digital twin is, kind of common term for many different, with many different meanings. Different people define digital twin in different ways. But what I mean by digital twin in this case is not just about the geometric information, but we need the physical information that we just need to know, what if you do this and you do that, we should be able to predict what's going to happen. And in the end, the bigger vision is the growing roads. Like we need to have a continuous and coherent construction and maintenance. We just don't build and construct, and they do it in the separate processes, but we need to put them all together so that we can, while you're building the roads, you should predict what kind of problem you will going to have, and then that's something we need to think about in the future of road industry. Okay, so this is the kind of digital roads framework we started thinking about, but of course this is not something we can finish in 5 years, or this is not something we achieve in the next 5 years, but we really have to think about the longer time scale, next 30, 40, 50-year landscape, and then what kind of other problems we have. So the future roads is actually trying to capture many other challenges. Of course, the baseline is sensing and thinking action process, but there are lots of other future applications that should come along with this, and that's the big idea of the work package 4 of this project. So there are lots of people involved in work package 4. So I learned a lot of things from our colleagues in Costain. Louis is one of them, but of course, Caroline and the other colleagues from Costain is very helpful. And the National Highway, we have lots of things since the time of writing proposals. And then we got the Industry Research Fellow Richard and the SRA Thomas. And then we got the new PhD student Sam starting from October. And that's the digital roads setup. Then we got the, very happy with the future roads, the first future road fellows, Arsen, joining from this September as well. Okay, so then I think I'm going to hand over to Thomas to explain a little more details about the work package 4 technologies. All right.
Thanks for me. Can you hear me? Yeah. Yeah, like Hume said, we are kind of outsiders to the field. So I'll give an interpretation of what we understood of this project with respect to work package 4. And I think our intention is to get your feedback on whether our interpretation is correct, or if you have other ideas and thoughts on this. A lot of it has to do with sensing. So most of it will involve sensing. And I will start with work package 4.2 because that seems like a more logical step. So it involves investigating what are the sensors that we will use in this project. And it involves the sensors that you need for developing the digital twin and also for maintaining it. And then develop these sensors if we need them, if you need to develop them, or use what are commercially available, and then establish benchmarking process to evaluate if these sensors are appropriate. We envisioned that there will be 3 strategies for sensing. The first one would be the ideal one, which is like you have a sensing system which can give you the best information possible, but of course it's going to be expensive. We envision that you won't be able to get the sensor information in real time. So you'll be discrete, as you can see with this line here, and you'll get it once in a while, and it'll take a lot of time to get this information. I will explain more in detail how these sensors would look like. And there would be another strategy which is using low-res sensors, which means they are not as accurate as the ones on the left side, but they will provide more continuous information, also more distributed. So you'll get multiple information from different agents that can be used to update the digital twin. So of course they're not as accurate, but you're getting multiple sources of information, which means you can combine them. Like Sumit said, even if you have 2 sensors which are of poor quality, if you can always combine them to get information which is always better than each of the sensor itself. And that's what we're going to leverage from that aspect. Then there's also another way of sensing, which is using embedded sensors. So these are sensors that you directly place inside your network on highways, for example. And then they will always provide continuous information, but they'll always be very low res and specific information. It's not necessary that these all sensors have the same type of information. There might be different modalities, but we need to figure out how to combine them to update your digital twin. Going more in details, so this is how the high-res sensing would look like, in our opinion. So you'll have these high-quality visual sensors. So this is the Trimple MX9, if people from Trimple are here. We'll use down-penetrating radars for getting more information about what is underneath your highways, LiDAR sensors for getting depth information, maybe thermal sensors, etc. Like I said, these are expensive. It takes a lot of time to get this data. You can't use these sensors everywhere in your road network. So you might use this once in a while to update your digital twin, and you'll get a very good representation of a digital twin, but you can't use it for real-time updating, because this, for example, Jonas was mentioned that this might take 1 year to completely map UK's highways using these kind of sensors. So if you want to update your digital twin, 2 years apparently. So if you want to update your digital twin, you can't rely on this all the time, but this would be your first step, right? So if you want a really good geometric representation, you would use this. And if you want to update your assets over time, you might have to rely on other type of sensors. So we envision that source will come from autonomous cars, obviously. Things are changing in this field. In this picture, you can see there are laser scanners, but we believe in the future there will be only cameras. So we're going to rely on cameras only for updating our digital twins, which is possible. It won't be as accurate as using LiDAR sensors. You won't get other modalities. For example, you won't be able to get thermal imaging. We'll have to rely on other sources for that. And finally, we'll have to use embedded sensors for certain modalities. For example, if I want to detect damages which are starting from underneath the ground, you can't rely on visual sensors. You'll have to use other type of sensors, and that is what our base group is trying to develop. But it might not be practical to use them throughout your road network, so you'll have to strategically place them and obtain information and connect them together. There are also sensors that are already available. We'll think of using them possibly. And the real challenge here is to combine different sensor modalities and obtain the best possible information, and think of what other sensing modalities I can use. For example, there might be non-trivial data like weather information or seismic activities that might actually be relevant for your digital twin. It is for us to investigate and figure out. So yeah, essentially this is how the big picture would look like. So you get this data from your high-res sensors, you update your digital twins, and then you periodically update your digital twins from your lower-res sensors. There is continuous data coming from your embedded sensors and discrete data from autonomous cars. And then there comes 4.1. So that's how the order we are following here. And that involves finding principles for detecting, essentially, how do I detect if something has gone wrong, and communicate that to the digital twin. And this involves mostly smart materials. You can also use visual sensors for detecting damage, but it's a problem which is already solved. So we will mostly be focusing on how do we use new smart materials for doing the same thing. And the reason why you would want to do that is you might be able to detect damage before it even happens, before it becomes severe. You can use cameras, but then most of the time you detect damage after it's reached a stage where you need to spend a lot of time and effort to maintain. We are not sure what you're going to use yet. It depends a lot on the materials that we develop. We have expertise already on this because we work on making robotic skins. So we do work a lot on tactile sensation and also detecting damage in our robots. So we have some translational skills that we think we can use. In essence, you might have to think of how do I get information from your sensors. So we need a way to integrate them, which could be either visual, electromagnetic waves, essentially acoustic or electrical signals, and then getting back the feedback from your materials after this integration. There are multiple techniques. I'm not going into details, but that's task 4.1. Once we develop these strategies, we need to test them. We could envision a platform where you create damages and then use the sensors to detect them. This is one example which is in France, I believe. We'll probably have a low scale system where we use robotic arms to create damage and investigate if we can detect where the damage is, or use commercial devices like Instance. So also once we develop this technology, we also need algorithms for detecting or for monitoring and detecting damages. Like I said, visual detection is pretty much a already solved task. The example is here. You can use deep learning techniques to figure out where there are damages. We actually have, by coincidence, worked a lot on damage detection. Like I said, we make robotic skins. We try to figure out how, if something happens wrong, how do we detect that? Multiple examples are shown here. So in this case, we're trying to figure out when we are trying to grasp something, if something goes wrong. There are learning-based techniques to figure out if something unexpected has happened, like Fumia said. So we predict what should happen, and if something goes against that, then you know something has gone wrong. And then we can identify where it went wrong and then backtrack all the way. And other examples of smart materials that can be used for damage sensing. I won't go into details, but the short story is we have some experience on detecting damage. Now we need to figure out how to scale this up to the entire country. And finally, the task 4.3, which is actually purely based on simulation, at least in the deliverable. The idea is to integrate our robotic platform to the digital twin. It might look like this. So this is an example from any robot, any robotics which has integrated this physics model of a quadruped robot inside a digital twin of a construction site. And this is more or less how we want our digital twin for the road network laws to look like. The difference, some of the differences here would be that the digital twin itself is purely geometric. There's no physics involved, but the robot has to have the physics-based modeling. So the tricky part is how do I integrate the physics that are in the robot with this purely geometric digital twin representation. And that part is not very trivial. We also need to figure out what kind of sensory modalities we need, what kind of feedback information you need for the robot, etc. And this is now only looking at inspection, and then there's the next question of how do I do maintenance with this digital twin of the robot inside the digital twin. And for that, you might need to develop physics model of materials itself. So if I want to apply smart materials on the digital twin road, I will need to have a physics model of how the materials behave under certain forces. How accurate our model needs to be is to be we are not sure how the answer to that question. It need not be as complex as the one shown here with like finite element models. We might need just a simpler model for our purposes, but that's something we need to investigate and figure out. As you can see, there was very little robotics, a lot of sensing and simulation involved. So we would actually also like to investigate what are the other possible areas we could cover with our expertise. One of the work which we actually recently did with one of our PhD students. So this is like a half-day work. We had heard that National Highways is interested in litter picking in highways. So one of our PhD students had actually tried to partially solve this problem by using a lot of deep learning techniques that are out there and a lot of data sets out there on the internet So this is an example of a robot which uses visual sensors to figure out what kind of litter is there, categorize it, and then pick it up and then put it in a garbage bin. So we are trying to investigate whether this can be scaled down to real world applications. Just because this is interesting and we have the time and the manpower to do so. Another example which is part of the future roads, so Arsen who will be working on this is interested in teleoperation. So we believe automation of this maintenance task would be very difficult. Teleoperation is probably the first step to do so, and this also fits in well with what Sumit was saying. So this can act like your data set, like your ground truth data set, so that your expert can learn over this data, so that this teleoperation data can be used by the robots in the future to generate the best control strategy or the control policy. So we are interested in figuring out how do we do this teleoperation cycle. So if I have a user which is staying inside the lab, how do I control my robot to do maintenance tasks, and also feed back to the digital twin. So give all this data to the digital twin so that you can update the digital twin later. We would very much like to know what are your problems or ideas that you think could be automated in this domain, and we will be here to discuss it with you afterwards. And that's it from us. Thank you. If you're interested, please.